Welcome back, and in this video we're going to be looking at pH and how to use concentrations to calculate the pH of a strong base. So we still need the same equation even though we're calculating the pH of a base, because pH remains the same. So if you remember from the last video, pH is defined as minus log to the base 10 of the concentration of the hydrogen ions. And with the higher the concentration of the hydrogen ions, the lower the pH, and the lower the concentration of hydrogen ions, the higher the pH. So expecting for an alkali to have a very low concentration of hydrogen ions, hence the high pH. To convert the other way, we've got concentration of hydrogen ions equals 10 to the minus pH. There's one more equation you need to know, and that is the ionic product of water, Kw, which is defined as the concentration of the hydrogen ions times the concentration of the OH negative ions. Now for a strong base, this equation is true, and it will always equal 1 times 10 to the minus 14 at 298 Kelvin. Obviously, if the temperature changes, this value will change, and we looked at that in the last video. So we're going to look at your notes, and we're on page 10. So we're asked what is the pH of a solution of 0.1 mole of sodium hydroxide. So we know from our Kw expression that Kw is the concentration of the hydrogen ions times the concentration of the OH negative ions. We also know, or we can assume because we're doing this at 298 Kelvin, that Kw is 1 times 10 to the minus 14. We know the concentration of the OH negatives, because that's the same as the concentration of the sodium hydroxide, 0.1. Rearranging our equation, we get the concentration of the hydrogen ions is 1 times 10 to the minus 13. So the pH is equal to minus log to the base 10 of 1 times 10 to the minus 13. So putting that into your calculator, you get a value of 13. So the pH of a 0.1 molar solution of sodium hydroxide at 298 Kelvin is 13. Working through the next example in the same way. So Kw is equal to the concentration of the hydrogen ions times the concentration of the OH negative ions. And because we're doing this at room temperature and pressure, we can assume that is 1 times 10 to the minus 14. So the concentration of the hydrogen ions is equal to 1 times 10 to the minus 14 divided by the concentration of the hydroxide, 0.02. So I'm just going to do that on my calculator. So it's 1 times 10 to the minus 14 divided by 0.02. And we get the concentration of the hydrogen ions equaling 5 times 10 to the minus 13. And again, I can do the pH of that. So pH is minus log of that number, my answer, and I get 12.3, and that's my pH. So working the last example through in the same way, we work out that the concentration of the hydrogen ions is 2.7 reoccurring times 10 to the minus 10. Again, I can work out therefore the pH by going minus log my answer, and we get a value of 9.56, and that's my pH. We can use the same idea to work out the hydroxide ion concentration given the pH. So we know that we've got pH of 12.4, and we know to work out the concentration of the hydrogen ions, that is 10 to the minus pH, because if you remember from our calculator, we've got the inverse. So log, and inversing that, you get 10 to the x. So we know from this, we can work out the concentration of the hydrogen ions. So we have 10 to the minus 12.4 as our concentration of our hydrogen ions. Kw is the same, it's 1 times 10 to the minus 14. Therefore, to work out the concentration of the OH negatives, it's 1 times 10 to the minus 14 divided by 10 to the minus 12.4. So again, I'm going to do that on my calculator. So I've got 1 times 10 to the minus 14 divided by, and I'm going to just put that in brackets, 10 to the minus 12.4. And we get our answer as 0.025. And that's moles per decimeter cubed as its concentration term. So the last two examples on this page, we want to work out the hydroxide ion concentration of these solutions. So we have a pH of 8.6, so the concentration of the hydrogen ions is equal to 10 to the minus 8.6. Therefore, concentration of OH negatives, rearranging my Kw expression, is going to be 1 times 10 to the minus 14 divided by 10 to the minus 8.6. And again, I can work that out on my calculator. And we get 3.98 times 10 to the minus 6. And again, that's moles dm to the minus 3 as we're dealing with concentration. So the last example, pH 7.4, again, concentration of hydrogen ions is 10 to the minus 7.4. Therefore, concentration of OH negative ions is 1 times 10 to the minus 14 divided by 10 to the minus 7.4. And again, we put that in our calculator. And we get 2.51 times 10 to the minus 7 moles per decimeter cubed of hydroxide ions. So just a little aside, looking at page 11, and this is using pKw. So what you have to remember is every time you see this little p term here, it basically means minus log to the base 10 of something. So if we think about pH, minus log to the base 10 of the hydrogen ions, we can use something like pOH, minus log to the base 10 of the concentration of the OH negative ions. So pKw, as you'd expect, is minus log to the base 10 of Kw, and that's the definition. So if we start with our Kw expression at 298 Kelvin, we can take logs all the way through. Now remember, if you have two terms here which are multiplied, they become addition when you're dealing with logs. So we get log of Kw is log of the concentration of hydrogen ions plus log of the OH negative ions, and that equals log of 10 to the minus 14, which just equals minus 14. Now if we multiply it through by minus 1, we're going to get minus log to the base 10 of Kw, which just turns into Kw, is equal to minus log of the hydrogen ions, in other words pH, plus minus log concentration of OH negatives equals 14. So we have another way that we can use Kw. So Kw is the pH plus the pOH, and that equals 14. So we can use either that expression or the expression on the previous page. It's really up to you which method you use to work out the pH of the following solutions. So I'm going to do two examples using the two different methods. You just choose which one works best for you. So using the method on the previous page, we know that Kw is equal to the concentration of the hydrogen ions times the concentration of the OH negative ions, and that is equal to 1 times 10 to the minus 14. So I can work out the concentration of the hydrogen ions equaling 1 times 10 to the minus 14 divided by 1, the concentration of the OH negative ions, and then pH is just minus log to the base 10 of that answer, which comes out as 14. So that's one way of doing it. The other way is to say that pKw, in other words 14, is equal to the pH plus the pOH. Now pOH is simply minus log to the base 10 the concentration of the hydroxide ions, which in our case is minus log to the base 10, 0.02. So doing that calculator, I get 1.69897, and therefore to find the pH, it is simply 14 minus that number, 1.69897. So the pH is 14 minus my answer, and it comes to 12.3. Either method is perfectly acceptable, Personally, I use this top one because this one works quite nicely, and I can use it also for water. This one again will work, but it's just another equation I've got to remember. So sometimes I find it personally easier to use this top one, but either of these methods works fine. Okay, so we're now on page 12 of your notes, and we're now going to look at weak acids. Now these are different, if you remember from the last video, from strong acids. Weak acids only partially ionize, or they only ionize to a very small extent. So if you have ethanoic acid in solution, it's mostly ethanoic acid. You've got very low concentrations of hydrogen ions, and you've got very low concentrations of ethanidioate or ethanoate ions. Now, this means that you can't just plug in the concentration of the acid and assume that it's equivalent to the concentration of the hydrogen ions, because so little of this has dissociated, unlike something like hydrochloric acid, which is mostly our hydrogen ions or our H3O positive ions and our chloride ions. For this one, we have to use a new expression. We have to use Ka, the acid dissociation constant. Notice this is not Kc. Please notice that water is never included, as it's always a constant in these expressions. So we need to add a new equation to the list of equations that we've got to learn. And this is the expression for Ka. So we're going to think about a weak acid, which only partially ionizes into our hydrogen ions and our anions. We can say that the Ka value for this is equal to the concentration of the hydrogen ions times the concentration of A minus divided by the concentration of HA. And we need to learn that expression. To calculate this, we're going to go through a calculation example on page 12. So this is the example we have on page 12, and I'm just going to go through it in a bit of detail. So we want to find the pH of a 0.01 molar ethanoic acid solution. We're told that the Ka for ethanoic acid is 1.7 times 10 to the minus 5 at 298 Kelvin. So the first thing I'm going to do is I'm going to do the dissociation reaction for ethanoic acid, which dissociates, remember this is reversible, into CH3COO negative and H positive. So the Ka expression for this is equal to the concentration of the salts times the concentration of the hydrogen ion concentration. Remember, this is what we want to find out because we're trying to find pH, divided by the concentration of the acid. Now, in order to calculate this, I need to make various assumptions. The first assumption I am going to make is that so little of this acid ionizes, because this is a weak acid, that I can say that the concentration of the ethanoic acid at the start, before this reaction has taken place, so at the start, equals the concentration of it at equilibrium. Now I can make that assumption, as I said, because this is a weak acid, so little of it ionizes, that statement is roughly true. Obviously, the stronger the acid, the more it will dissociate, the less true this statement becomes. But for weak acids like ethanoic acid, it's a good enough approximation. The second assumption I'm going to make is that the concentration of the hydrogen ions equals the concentration of the CH3COO negative. That's at equilibrium. And that one's pretty much always going to be true for a monobasic acid, because here it dissociates into a 1-to-1 ratio. So the concentration of this and this will always be the same. The last one, and I'm just drawing a dotted line because it's kind of related back to some of these bits, the concentration of the hydrogen ions from the water is negligible. Can't spell. Negligible. In other words, I get so little hydrogen ions coming from the water, because remember the concentration of hydrogen ions of pure water at 298 Kelvin is 1 times 10 to the minus 7, that I can ignore it. So I can assume that the concentration of the hydrogen ions is purely determined by the concentration of the salt and vice versa. So I know that those two numbers are the same. Now, if you're asked for assumptions, and you quite often are in these two questions, do stick to these first two. If it asks you for a third assumption, that's when you bring this last one in. But these two assumptions are kind of related, and this one's a better one to go for because it's giving us the concentration of the hydrogen ions. So we can now put those assumptions into our Ka expression, and we can put in some numbers. We know that Ka is 1.7 times 10 to the minus 5. We know that these two concentrations are the same, so I'm timesing two identical numbers together. In other words, I'm squaring it. So I can say that those two together equals the concentration of the hydrogen ions squared, divided by the concentration of the acid, and that's the concentration of the acid at the start, which is 0.01. Now all I need to do is to put some numbers in my calculator and solve. So the concentration of the hydrogen ions is equal to the square root, because I've got to square root everything, 1.7 times 10 to the minus 5 times 0.01. And then it becomes a straightforward calculation. So putting these numbers into my calculators, I get the concentration of the hydrogen ions here, and then I can use my expression minus log to the base 10 of that concentration to find the pH. So the pH comes out in the end as 3.38.